Here I compare a linear progression to an exponential progression, and one reason that we confuse them is they look very similar at first because you're doubling little numbers. Exponential growth can even be sublinear at first, but ultimately it profoundly diverges from the intuitive linear perspective. And the ongoing exponential growth is made up of a series of S-curves reflecting different technologies. One of the objections to my thesis is that Kurzweil takes these exponentials and just projects them out, and we all know exponential growth can't go on forever. But turns out that in information technology, once we reach the end of the line for a particular paradigm, the research community turns to creating the next paradigm. There's research pressure to create the next paradigm. And the ultimate resources needed to compute a bit or transmit a bit or to remember a bit is so vanishingly small that we can keep this process of going from one paradigm to the next and having a cascade of S-curves for a very long time. In the case of computation, we can see our way to doing that until late in the 21st century when these technologies are trillions of times more powerful than the human body and brain. So if we look, for example, at computation, it's not just Moore's law. People think this exponential growth of information technology is Moore's law. They call it Moore's law. Moore's law is just one paradigm among several in computation, and computation itself is just one example of many of this exponential growth of information technology. Here we have over a century, going back to the 1890 census, of history of computers. And this is MIPS per dollar, and it has grown exponentially for, in fact, it's a double exponential because on a logarithmic scale, a straight line is exponential growth. So we have another exponential here. It took 3 years to double the price performance of computing in 1900, 2 years in 1950. It was 12 months in the year 2000. It's now down to 11 months. But look at how smooth a trajectory this is. Now, this hides the scale because every level on this graph is 10,000 times greater than the level below it. So this reflects trillions-fold increase in the amount of computation you get per dollar, inflation adjusted in a century. A billion-fold just since I was an undergraduate at MIT. But the most amazing thing about this graph is look at how smooth and predictable a trajectory this is. We have this graph through 2002 in my book, The Singularity is Near. What you're looking at has been updated to 2008. And you can see it has stayed right on course. In fact, I've been making these forward-looking predictions for 30 years. And nothing affected this. World War I, World War II, the Cold War, the Great Depression, a lot of the recent economic downturn, none of that had any impact on this inexorable exponential growth, doubly exponential growth of computation. And it turns out this is true of every other form of information technology as well. Cost of a transistor has come down smoothly, exponentially. You can get one transistor for $1 in 1968. You can get a billion today for $1. But again, look at how smooth and predictable a trajectory this is. And as we've made them cheaper, they're better because they're smaller. And they have less distance for the electrons to travel. So they're faster. And the speed has gone up. The cost of a transistor cycle has come down by about half every year. That's a 50% deflation rate. And the economists worry about inflation or deflation. But we actually more than double our consumption of these technologies every year because when price performance reaches a certain level, whole new applications explode on the landscape. So here's bits shipped, but you could measure any other form of information technology. There's actually been 18% growth in constant currency every year for the last half century, despite the fact you can get twice as much of it every year for the same cost. In fact, this is what is driving economic growth. Biotechnology revolution I was talking about, but DNA sequencing costs coming down by half every year, the amount of genetic data doubling every year, and many other aspects of biology are scaling up in a similar fashion. Communication technology, deeply democratizing, many different ways to measure this. This is bits being moved around on the internet. We've had exponential growth in the total capacity of wireless networks going back a century to Morse code wireless transmissions up through the G4 communications of today. and that's going to continue indefinitely. Ultimately, we will send these devices in our bodies and brains. We'll have billions of them. They will be computing, but they'll also be on the cloud. So if you talk to someone in 2035, you'll be talking to someone who's thinking with biological intelligence as well as non-biological intelligence. And the computers in their brain will be out on the cloud. So we'll be thinking out on the cloud, and we'll be able to communicate with each other out on the cloud. We'll have things like full immersion virtual reality from within the nervous system. We're shrinking technology at an exponential rate, which I mentioned, and that is really driving this nanotechnology revolution. And we're building these systems. There are now dozens of animal experiments, and some of which have been presented at this conference. We're performing already measurable therapeutic interventions in animals. Some of these devices are fairly simple. They're either nanoparticles or nano cages, nano containers that can release medications in a certain program fashion. The sophistication and scale of complexity of these devices is going to scale up exponentially. These devices will be really 1 billion times more capable in price performance in 25 years. They will be very sophisticated with computers. They'll be communicating with each other. They'll be on a wireless local area network. They'll be on the internet. And they will be able to greatly augment our biological capacity. We'll have nano-engineered white blood cells that can detect pathogens, download software to combat them, and do that in seconds rather than hours, as I mentioned. This is a video of Rob Freitas's nano-engineered red blood cell, a erythrocyte. And as I mentioned, these will be thousands of times more capable than your biological systems. And we'll be re-engineering all of our systems using nanotechnology over the next several decades. We'll have plenty of computation as we go through this century. We'll be gaining the software insights from reverse engineering the human brain. We're increasingly using nanotechnology to increase the precision and scale of scanners. Non-invasive brain scanning is doubling its spatial resolution every year. The amount of data we're getting from these scanners is doubling every year. And we're turning this data into working models and simulations of brain regions. This is a block diagram of the auditory cortex. That's one of the visual cortex, the cerebellum, which is an important region comprising half the neurons in the brain. That's where we do our skill formation, has been modeled and simulated. That's how we catch a fly ball. It controls our skill formation. We always wondered how a 10-year-old does that, because she has to solve a dozen simultaneous differential equations to catch a fly ball, and most 10-year-olds haven't taken calculus. We always wondered, how does that work? Well, the cerebellum actually does solve those equations. It collapses them using a mathematical process called basis functions, and we've actually reverse engineered that and simulated it and tested those simulations, and it works similarly to human performance. Most interestingly, projects like the Blue Brain project under Henry Markram are simulating substantial slices of the cerebral cortex. I was on a panel with him recently at this Israeli presidential conference, and I was actually the conservative on the panel because he expects that he will have a full human-scale simulation of the cerebral cortex by 2018. That may happen, but I think it'll actually take some more years to get it to work effectively, and we're actually also going to have to learn how to train it, because actually learning and education is part of the human brain's paradigm. So I'm sticking with 2029 for when we really will have reverse engineered the human brain, understand its principles of operation, re-implemented it with systems that can pass the Turing test. And the primary application is not some alien invasion from Mars to compete with us. We're going to use this technology the same way we use technology today, the same way I use this, even though it's not yet in my brain. It is making me smarter. I can access all of human knowledge with a few keystrokes. And we're going to put these devices in our brain. We're going to augment our own intelligence. That's always been the role of technology. Ever since we picked up a stick to reach a higher branch, we've extended our reach with our tools.